Hello, we are Vanessa, Regina, Daniela, and Tali. We will demonstrate our Mariotte bottle experiment and we will investigate how the position of the straw affects the water outlet velocity.
Mariotte principle states that a liquid outflow from a sealed container with an air inlet tube remains at a constant rate, regardless of the liquid level in the container. This is because the air pressure inside the tube remains constant, maintaining a steady hydrostatic pressure at the outlet.
The Marriott bottle is a special type of reservoir designed to provide a constant flow rate of liquid. It must have the following characteristics. It must be a sealed container, have a vertical tube that extends into the liquid, and an outlet at the bottom. For our experiment, we used a container that sealed the top by rotating it. We used a straw as the tube, and we just drilled a hole at the bottom of our container. How it works is really simple. As liquid flows out from the bottom, air enters through the tube. The air pressure inside remains constant, balancing the hydrostatic pressure at the outlet, which creates a steady outflow rate that does not depend on the liquid level until the liquid level drops below the bottom of the air tube. Then it behaves like a normal container and the flow decreases.
Our key equation is V
Mid-level
equals to root
position,
square of
notice that the water outlet
2GHEFF, where
velocity
HEFF
remains
is effective water
unchanged
head.
compared
This
to
equation,
figure
along
1.
with reference
The
such as
straw
Marriott's original work and White's fluid mechanics, underpoints our analysis.
So I think that when the straw is at the top, the pressure head should be the highest, resulting in a strong and fast water jet. Then when the straw is midway or in the middle of the bottle, slightly lowers the pressure head. So the water speed should be like a bit lower than at the top. Now when the straw is slightly above the outlet hole, like the pressure difference is smaller, so the water flow slows down noticeably compared to the previous positions. And when the straw is exactly at the outlet hole, the effective pressure is almost like negligible. I expect the water outlet velocity to be very low or even nearly.
This is the first case where we put the straw at the top. Here, the straw is inserted at the very top of the bottle. As you can see, the water flows through the strong, steady stream. This confirms our prediction that using the full water column provides the maximum effective head and the highest outlet velocity. This is the first case where we put the straw at the top. Here, the straw is inserted at the very top of the bottle. As you can see, the water
We adjust the straw at the mid-level position. Notice that the water outlet velocity remains unchanged compared to figure 1. The straw is still fully submerged, maintaining the internal pressure and the effective head. We adjust the straw at the mid-level position. Notice that the water outlet velocity remains unchanged.
Case 3. In this final clip, we lower the straw so that it's exactly at the outlet level. Observe how no water flows out. This happens because the effective water head half is completely lost, and there is no pressure to drive the water out. Same as our equation predicts. My results confirm that the strongest and most consistent flow occurs when the straw is at the top, with very similar outcomes at mid-level. And the most significant difference appears when the straw is at the outlet level, where no water flows, because of the effective water head vanishes. This shows that the outlet velocity is directly linked to the effective pressure provided by the water column.
The velocity is the highest and nearly identical when the straw is at the top and the mid level. The biggest difference is that at the outlet level there is no water flow. These changes are caused by the effective water head. When the straw is submerged, it is maintained, but when the straw is at the same height as the outlet level, it is lost, eliminating the pressure necessary to drive the flow, as indicated by the equation. We hope our experiment helped you understand these topics better. Thank you.